right, so today we're going to be looking at lesson 7 and 767. And this lesson has us looking at things called hanger diagrams. So we have been using tape diagrams to look at all of our equation work, and now we're going to be looking at hanger diagrams. So what are some things that you're noticing as you look at the picture? Please type in at least one or two things that you notice and one or two things that you wonder. So go ahead and pause. Okay, one thing I noticed is that over here, the pink socks are showing a balanced hanger because it's straight up or straight across, right? So this is showing me that these two socks weigh the same amount. Whereas this hanger does not look balanced, and it looks like there's something in this sock weighing it down, which makes sense of why this sock would be lighter. So if it's balanced, we can see that they're showing that they're equal. So both sides are equal. This is unbalanced, showing us, oh, this side is actually heavier than the other side. And as we do our hanger diagrams, you're going to see some similarities. So let's jump in and take a look. If we look at this hanger diagram, just like our blue socks, this is not balanced. This is showing us that if it's slanted down, this side is weighing down more than the left, right? So enter a value to balance the hanger. So what do we have to add to 3 to make it equal to 8? Well, 3 plus 5 equals 8. So x has to equal 5. Okay? Now, explain our thinking. Well, I kind of just did, right? 3 plus 5 equals 8. And we know that this side is 8, so the x has to be 5. So now let's take a look at this. Which equation describes the hanger? Well, again, balanced means that this side equals, that's a big clue, this side, right? And I'm going to be honest, we can actually look at this, and I'm going to show you down here. I'm going to show you what it looks like as a bar model or as a tape diagram. So for the tape diagram version, we know the total is this 8 because we just have an 8. So we know this is 8. And we know that on the other side, there was an X and a 3, right? So this is telling us we don't have 3 X's, we have 1 X and a 3. So that's X plus 3 on one side, and it's equal to 8 on the other side. So this particular hanger diagram shows X plus 3 is 8. Okay, and then we can explain that, right? We don't have 3 X's. We're not dividing anything by 3. And we're not subtracting. We have two things together equaling 8. So let's go to our next one. Again, this is unbalanced. We have 12 over here, and then we have 2 Y's here. So what can we put in for Y to make it equal to 12, right? Well, if 12 is equal to 2 Y's, again, I'm going to show you the bar model version just so you can make some connections here. That's telling us we have 12 and we have 2 Y's, and each Y is equal. So if these are equal, what has to be in each one to make 12? 6, right? Because 2 6's is 12. So Y equals 12. For those reasons that I just explained, right? 2 6's, whoops. That's interesting. It says no, that doesn't equal 12. Well, let's go back and look at our other one. Interesting. I'm noticing some coloring differences. Let's try something here. Oops, because I put in 12. Should be 6, right? There we go. All right, so we know each one is 6 because there's 2 equal Y's that make that up. So which equation does this describe? Well, we know 12 is equal to 2y's, or 2 times y, right? So it's this one here. We're not adding y and a 2, right? That's like the first one. We have 2 y's, so there's 2 times y, okay? So we can add that in. Let's see here. The one side 12 is equal to 2 y's, which means 2 times y, or just 2y would be the same as well. All right, so let's try this out. This is an Are You Ready for More, which means that it is a challenge, right? So give it a try to see how you do. It says find values for X and Y so that the hanger balances. Press try it to see if the hanger balances. So you're going to try to see if you know what it is. And we're going to type in the answer and then hit try it to see if it works. So when we're looking at this, so I'm just trying to think here. Okay, so here's our equation. This is interesting. So gosh, 2x plus 3. Well, what if we just make x something? What if we make x worth 2? I don't know. That means this is 2 and this is 2. So 2 and 2 is 4, plus 3 is 7. So then that means y has to be 7. Let's try it. All right. Looks like it works. And then we can try another. So again, we can put in a value. What if we put in a value for y? Let's try it the other way. Let's make y equal to, I don't know, let's say 15. If y is 15, what's my x going to have to be? Right? So let's see. Y, well, that means this all has to equal 15. So, okay, take 3 away. That leaves 15 minus 3 is 12. That means these both have to be 6's, right? 6 and 6 is 12. 12 and 3 is 15. So let's see. So 6. Let's see. All right. Very good. So there's lots of different values we could use. So now we've got one, and I know this one might be a little hard to see, but it says write an equation for the hanger diagram in the box, then use the sketch to show how to solve the equation algebraically. So again, one side of the hanger is equal to the other side, right? So we have 1, 2, 3, 4, 5, 6, 7. I can add up all those because they're all numbers. So we have 7 equals, and then we have 1, 2, 3 W's. So that's 3 W's plus 1. Okay, so equals 3 W's plus 1. There's my equation, which I got right. Now it says solve it, meaning what's W, right? So when I'm looking at this, and again, I do want to give you an example of a bar model because that's what we have been using and I want you to be able to make a connection. But if we use the bar model, we're saying, oh, look, we have 7 here. The whole thing's worth 7, right? And making up that 7, you have a 1, but then you also have 3 W's, okay? So then you have to start thinking about how you would solve that, right? So I know over here, to keep this balanced, this is another way we can start looking at equation work, is using that whole concept of being balanced, right? So when I'm looking at this, I'm noticing there's ones here and there's ones here. So if I take a 1 off of the 7, right, that would, on the bar model that we've been doing, that's like saying, oh, let's get rid of the 1. That means that's going to be 6, right? Because there's 6 left here. And then that's the same as getting rid of this 1 over here, right? We've taken a 1 from the total and from the actual things that make it up. So that tells us that there's 6 left on one side and that those 6 ones are equal to 3 W's. We want to know what just 1 W is. So if I break the W's into 3 groups, we have to break the 6 into 3 groups. That means there's going to be 1, 2, 1, 2, 1, 2, 2 in each group, right? So each W is worth 2, which is what we did here. what we have been doing, right? Oh, well, it's got to be 2, 2, and 2. So W is 2. Okay, and then we can do the same thing for here, the equation. I'm seeing 2z's, so we have 2z plus 3 equals, and then over here we have 1, 2, 3, 4, 5 equals 5, right? So algebraically, how could we use this, right? And actually, I'm going to show you over here. So 2z algebraically means using, we should have done this for the other one. It means using the equation, not necessarily just this hanger diagram. So let's go back to the other one actually and show that. When we did 7 equals 3w plus 1, the first thing we did is we subtracted 1 from both sides, right? So we did minus 1 from this side and we got 6 is equal to, and then we took this 1 off here, right? And we left 3w. So then we were left with 6 equals 3w. And then we actually divided, and I'm going to use the fraction bar even though it's a little confusing with that. So 6 divided by 3, because that's what we did. We divided the 6 by 3, and then we divided 3w by 3, the 3 w's by 3, and we got a w, right? Each w was equal to 2, right? So let's look over here. On this one, what can we do first? Well, I'm noticing let's get rid of 3 from this side because we want to know what just this one z is, what one of those z's is. So if I take 3 off of this side, that's saying 2z plus 3, well, we're going to take away 3. So get rid of that. That means we're left with 2 z's, right, on this side. But since we took 3 from here, we also have to take 3 from here. So let's do that. So 5 minus 3 is 2. So now we're left with these 2 z's are equal to 2 wholes, 2 numbers. So, well, what does z have to be to equal 2? Well, if we cut 2 z's into 2 equal groups, we can cut the 2 into 2 equal groups. So now we're dividing 2 z's by 2. We got, in each group there's a z. We divide 2 by 2 and we get 1. You've been doing this in your bar models, by the way, right? That is just showing, let me show you on the bar model how you've been doing this because it's the same thing. You're just now writing it out, okay? What you did here is you knew this was 5 and it was made up of 3 and then 2 z's, z and z. And what you did is you would look at this and go, oh yeah, let's find out what just the z's are. Just the z's are 2, right? Right? 5 minus 3 is 2. And then you thought, oh, well, what has to be in each box? When you take this 2 and you chop it into 2 groups, what's in each group? 1. So z is 1. You've done the same thing that you've been doing. Okay? Let's try another one. Over here, again, we have 1, 2, 3, 4, 5, 6. So we have 6 is equal to 2y's. So 6 equals 2y's plus 3. Right? And let's type that in. 2y plus 3. All right. And now we have to solve, right? So when I'm looking at the equation, see, I'm going to try to transfer you from doing pictures to equations. I'm noticing that extra 3 over here, doesn't need to be there. So we're going to get rid of the 3 on here, right? So we're going to take the 3 from this side, which leaves us with 2y. That's the same thing when we look over here and we go, oh yeah, let's get rid of these 3. And to keep it balanced, if we take 3 from one side, we got to take 3 from the other side. So we're going to do 6 minus 3, which left us with 3. 1, 2, 3. So now we know that 3 is equal to 2y's, right? So now, and again, I'm going to take you back to your bar models because that's what you have been using. And it, whatever works for you, right? The hanger diagrams show what's happening when we do things algebraically, maybe a little bit better than the bar models. So here's what we do. Again, we started with 2y's plus 3, and they equaled 6. What we had just done is we figured out, well, what are just 2y's worth, right? 3. So now we've got this number 3, right? But we need to chop it into 2 equal groups. So if you chop 3 into 2 equal groups, well, you're not going to get a whole number, are you? Well, 3, and if I divide it in half, I'm really just dividing this 1 in half. And now I have 2 groups, right? I have 1 whole and a half, 1 whole and a half. Cool. And the y's are, they're already chopped into 2 groups here. So basically this is 1 and a half. Y is 1 and a half. Because 3 chopped into 2 pieces, 3 wholes divided into 2 is 1 and a half. So y equals 1 and a half. Okay. Oh, and to show that here algebraically, you continue with what you were doing, right? You would take, here we have 2 y's. We want just 1, so we're going to divide it by 2. Really, my y is switched. It's over here, right? So 2 y's divided into 2 groups is 1 y in each group. And then 3 divided by 2, well, lo and behold, 3 halves is 1 and a half, isn't it? 3 divided by 2 equals 1 and a half, which we can show in both pictures. Let's try another one. Okay, equation 3x's plus 2 equals 3. Okay, I'm going to slowly transition. So I'm going to look at this one first. I'm going to look at the equation first, and then we'll do the picture work. Okay, so again, I want to end up finding what just 1x is. So if I get rid of these 2 here, that's going to help me know what just the x's are worth, right? So let's take 2 away. We're going to get rid of that 2, which on this side of the equation leaves us with 3x, right? And if I take 2 from this side of the equation, like this, getting rid of those 2, it's unbalanced. So I'm actually going to take 2 away here. And that means we're left with 1 on this side of the equation. So algebraically, we know 3x's is equal to 1 whole. Well, I don't want to know what 3x's are. I want to know what 1x is. So we're going to divide those 3x's into 3 equal groups, right? So 3x literally divided by 3 is going to give us an x in each group, right? But if I take 1 whole, I actually have to divide the whole into 3 groups too. So it's going to look weird, but it would be like, I'm going to use this line. It would be like, okay, there's a third. It's a little, so we chop the whole into 3 groups, which is the same thing as doing, well, gosh, 1 divided by 3 actually equals 1/3. So each x is a third, right? If you have a whole and you chop it into 3 equal pieces, you're going to have 1/3 in each piece. All right. Let's try this one. For this one, we've got 2y. Now they've done something a little different. They've shifted, instead of putting a bunch of 1s, instead of putting 10 1s, they put all the 1s together, which is just fine. It's the same. 2y plus 10 is equal to 31. So again, we're going to do some things to make this equation balanced, right? So 2y plus 10. Well, I want to know what just 1y is. So let's get rid of those 10s, the 10. So we're going to do minus 10. We're going to end up with 2y's equals, well, if I took 10 off here, I got to take 10 off of here, which makes this going to be 21, right? 31 minus 10 is 21. So now I know these two y's is being chopped up. Well, the two y's equals 21, right? We want to know what just one y is. So we're going to chop them both into equal groups. So 2y, we're going to divide it into two groups. So we get y. And 21 divided by 2, you could do this different ways, right? You could do mixed number because this literally is 21 halves. That is a correct answer, actually. But 21 halves is also, let's see, we could make 10 wholes, right? Because if you have 10 wholes, you would get 20 pieces if they're chopped in halves. But then we have one piece left. So it's 10 and a half. Or if you wanted to use your calculator, it's 21 divided by 10. Or I'm sorry, 2, not 10. And it equals 10.5, which is also the same thing as 10 and a half, right? So lots of ways that you can do this. Okay, make sure you're putting your equation work in here. The 2y plus 10 is 31. Let's try this one. So the equation that we're seeing, it's getting a little difficult each time, right? They're adding decimals. It's the same. Don't freak out. So we have 6.8 is equal to 2z's, 1, 2, z plus 2.2. So again, the whole thing that we're trying to do, we're going to keep our equation balanced. We're going to keep our hanger balanced. We're going to get rid of the 2.2 because it's with the two z's. So we're going to take 2.2 off of this whole side, leaving us with just 2z on one side. And then if we take 2.2 off of 6.8 minus 2.2, you could use a calculator. I think for problems like this, it's kind of easy. It's just 4.6. You could still use a calculator. That's fine. So now we know this is not 6.8 over here. We've got 4.6. And we want to know what's one z worth, right? So if we have two z's, we're going to divide them into two groups, which means we're dividing them by 2, which gives us a z in each group, which means we have to divide 4.6 into two groups. You could use a calculator, or you could know that 4.6, 4 divided by 2 is 2, and 6 divided by 2 is 3. So 4.6 divided by 2 is 2.3. So therefore, z is equal to 2.3. Okay. All right, now fractions. Again, don't freak out. These are actually easy fractions because I'm noticing they both have halves. That just means we're talking about the same size piece. 17 halves. That's like saying if you have 17, if you have a pizza, right? You have a pizza, you cut it in half. That's 2 halves. Well, you don't have 2, you have 17 of those, right? So that's a lot of pizzas. That's 8.5 pizzas. So let's go ahead. Let's continue. It's the same thing. We've got 4 W's plus 3 halves. All right. Equals 17 halves. All right. We want to know what just the W's are, right? So we're going to get rid of the 3 halves on this side, which means if we take 3 halves off of this side, we're left with 4W, which equals, well, we have to take the 3 halves off of this side or it's unbalanced right now. So this isn't 17 halves. We actually have to take 3 halves off. So if you have 17 halves, I'm going to do this, 17 halves minus 3 halves. You're still talking about halves. Nothing changes here. 17 minus 3 is 14. 14. Whoops. 14 halves, right? So we know 4 W's is equal to 14 halves. Does anybody know anything about 14 halves? You could put this in the calculator just fine, or you could know that that's also 14 halves. If you put those halves together and you have 14, you got 7 pizzas. So that's actually equal to 7. So we know that we're left with 4 W's being equal to 7, right? But we need to know what 1 W is. So we're going to divide 4 W's into 4 equal size pieces, which means we've got to do the same thing over here to the 7. So we are ending up with 7 divided by 4. We're doing 4W divided by 4, which gives us just a W. So 7 divided by 4, 1.75. So that means W is 1.75, or you could write it as 1 3/4. That is the fraction version of 1.75. Okay. So the question is, draw a hanger diagram to represent the equation. How was solving the equation and diagram alike? How was solving the equation and diagram different? So what they mean is this is solving the equation. The work we're doing, the work we're showing here, and what we're doing on the diagram, that there's similarities, right? So for this, a hanger diagram. All right, so we've got, here's our hanger, right? 4x. You can put it in a box. It doesn't matter if you do or you don't. 4x plus 6, right? I've got 4 x's and I got 6. Over here, I'm just going to put 9.2. We know they're equal. These are equal. It's balanced. So solve for it. Okay, well, 4x plus 6 equals 9.2. The first thing I'm going to do is I'm going to get rid of my 6 here, right? And if I get rid of 6 here, I got to get rid of 6 over here, right? So that means we're left with 4x is equal, and then 9.2 minus 6, well, that's 3.2. Okay, so how is it alike? Well, I noticed that we're always taking we're doing the same thing to both sides, right? On the diagram, it's got 2 sides to the hanger. Our equation has 2 sides, doesn't it? So I'm noticing that we are always doing the same thing to each side of the equation and each side of the diagram. If we add on one side, or we haven't been, if we've been taking away from each side, we take away from both sides. If we divide, like we're going to do next, we have to divide the x's into 4 groups. We got to divide this into 4 groups, right? So we're going to end up doing divided by 4, divided by 4. So 4 x's divided by 4 gives you just an x. And 3.2 divided by 4 gives us 0.8. Okay? Now, how is solving the equation and diagram different? Well, we're actually physically taking away. I would say the one thing I'm noticing is when I divide on the equation, I am not actually making groups, right? I'm kind of doing that on the calculator, meaning I'm not physically, before I was physically taking away, right? When we take away the 6, we actually get rid of the 6, right? But then when we divide the 4, it's kind of like more in our mind, right? I'm not physically, let's see, dividing. Okay? And you might find something different, all right? So the main idea here, that our lesson summary for this is basically when you're using diagrams, hanger diagrams, you've got balanced sides, right? And anytime you do something to one side, you do it to the other. And with hanger diagrams, the whole concept is thinking to yourself, we want to get that variable into a group by itself. Okay? Which is a little bit different from what we had, the way we were thinking when using bar models. Okay? And that is it. You are finished with lesson 7.